Hey guys, this is Donnie, and today I'm going to be giving a pretty in-depth overview of C# methods. There is a lot of material in this presentation and the code that I have to go along with it, so I'm going to try to get through it quickly. I apologize if I go a little too fast, but if I don't, this is going to take over an hour, so I will do my best. This is a table of contents, basically, just a kind of a guide through this presentation as I go. So I just wanted to show you before we start going through this that what we're going to be covering here is in my GitHub account, which is, as you know, GitHub with my name, Donnie Santos. If you go into the 1050 repository and into the 2022 folder, which contains the new content I'm building, this is the solution that we're going to be working with. In particular, this project, part 8, methods. So all the code that we're going to be looking at today is in here in GitHub. Also, it is in .NET Fiddle, which exists, ironically enough, also in links inside of the code that I have on GitHub. So if you are not in my class and don't have links to the .NET Fiddle code, uh, the links to the .NET Fiddle are actually inside of the code on GitHub as well. So I have that solution open here. As you can see, I have the project part 8 methods expanded, and I have this class person opened up and collapsed to all of the definitions in the class. All right, so with that, I'm going to dive into the meat of this presentation, and remember, it goes along with the code that I have open in Visual Studio. I'll be referring back to that as we go. Okay, so here's the table of contents. And the first slide is just talking about what is a method. We've already gone over functions, and basically a method is just a function with context. That's my very simple explanation of it. That's far from a good definition, but I want to give you something to start with. So we're all familiar with how to write a function, um, whether or not it can be void, whether or not it returns a value, how to pass it parameters, and all of that stuff is going to translate over into what we're talking about here. So as you know, I've always been telling you once we started object-oriented programming, everything in OOP happens within the context of an object, or if it's static, in the context of a class. So that means things don't happen nowhere. They happen because something is doing it. And attributes don't hang around nowhere. Attributes belong to objects. So this definition from Wikipedia, I think, explains that a little in a little longer phrase. A method in object-oriented programming is a procedure associated with a message and an object. So that's computer talk for we're telling an object to do something. And the next line is an object consists of data and behavior. So you can see there they're saying with behavior, we're telling the object we want it to do something. And these comprise an interface, which specifies how the object may be utilized by any of its various consumers. Now we've talked about this concept of an interface before, especially with the microwave example. So, a complex object with a lot of complex stuff happening on the inside, but a very simple public interface, which would be like the buttons on the front that allows people to use it easily, even though it's complex and they wouldn't be able to understand how it works internally. They can use it from the outside, quite simply with a simple interface. So an object consists of data and behavior. Now that's both internal and external. I would have probably said that the public pieces of data and behavior comprise the interface, but that's okay. Data is represented as properties, or you can call them, we know them as variables right now. Properties are a little bit more, they're basically variables with a fancy accessor. And behaviors are represented as methods. So um, usually I tell people classes define nothing but variables and methods. So that's the data layer and the behavior layer of an object. So what does an object, what are the qualities of an object? Like, for a human being, it would be like hair color, eye color. And what are the behaviors of an object? So for a human, it'd be like walk and talk. I have, in other words, classes define variables and methods that belong to itself or its instances. The variables are the state, like the attributes, the nouns, etc., and the methods are the behaviors, action verbs, etc. Here I've provided kind of a proper function that belongs to an object. So that's what the title means when it says a method as a function with context. So when you look at the code on the left where it says public int give me your age plus this number, it takes a number and it returns this dot age plus number. That function, give me your age plus this number, I'm going to call it a function for now because this is actually a function. Remember what a function is. A function takes input and it does something, does some type of uh, computation, and then it provides an output. And this certainly does that. Um, the difference is this function is defined inside of the class, just as we have been defining our variables. So just like age is a variable inside of any person object that you would create, give me your age plus this number is a function that would be part of any um, person object that you instantiate. So if you create 10 people, they're all going to be able to perform the behavior, give me your age plus this number. So on the right, you can kind of see me represent this visually with uh, the private variable being kind of on the inside of the microwave, and the method being how you use the object, like the buttons on the front of the microwave, because age is private in the class, but the method is public. Now, there is one thing that I want to note that is going to come into play in the next couple of slides, is that when we were doing functions before object-oriented programming, the only thing they had to work with was the parameters. Basically, a function took parameters and returned an output. Now, a function, by true definition, there's something called a pure function. A pure function uh, takes inputs and returns an output and doesn't do anything else. Like if it does anything else other than produce a brand new output based on the inputs, then it's no longer quote unquote pure. Like if you if you change any type of state or variable value that persists after the function is over, that's called a side effect in functional programming. So there's this concept of a pure function. Now this function is not pure, because as you can see in object-oriented programming, um, we have states. So all people have an age, and your age doesn't go away. It stays there on the object. And you'll notice that this particular function is not just a function of number, it's a function of number plus this dot age. So that's a combination of two different things. It's a combination of one, a parameter that's given, and two, a part of my, a piece of information that's already known about myself as an object. So I'm going to get into the analogies. That's hopefully what I'll spend the most time on to try to make it intuitive. But if you're asking me, Donnie, how old are you, and then add 5 to that. That's kind of like this question. So it's like you would be asking me two things basically. First of all, you're asking for my age, which I already know. So I know that part of the answer, but I don't know the number that you want me to add to it. You're telling me that. So you're saying, here's 5, a number I'm giving you, which I know, but you didn't know yet. But I also want you to add that number to your age, which is something that you know but I don't know about. So the age is internal to the object, as you can see over here on inside of the internal state in the picture on the right. So this is very key to understanding almost everything that we're talking about here. Since this is no longer just a function that's floating in outer space. Now it's a function that has context. Since it's declared inside of the person class, it will be available for all of the people objects. Therefore, inside of the method, it has access to the parameter values as well as its own member values, like in this case, age. That means you have the power, even if you shouldn't, it means you have the power to change those values. Like I could write a line of code that literally, right above return this dot age plus number changes the person's age. Well, that wouldn't be good because that's not what the function says it's supposed to do. It doesn't say change your age. It says give me your age. So you know, that you have to combine what you are allowed to do with what you're trying to do, and it has to be logical. It's the language is not going to protect you from being illogical. You could write a function or a method function that it doesn't do at all what it says it's supposed to do. So this is kind of the very quick and dirty intro, and hopefully if you understand this, like this is the core, which is just taking what we learned in functions and moving that into the realm of a world where we have context. So it's now not just a function, it's a function that belongs to an object. And more than that, that object has state that is known inside of the logic of the function. So that's the key. We're combining what we did before with the parameter values with also knowledge of our own internal member variables. And you don't have to, but I strongly advise using this before specifying the member variables. It just calls it out for sure to say this is a member variable. And the last thing is, at the bottom left, you'll notice since age is now private, you can't, if I try to say person.age plus 5, it won't let you because of the accessibility level. So you usually want everything to be private unless it needs to be public. So in this case, the age does not need to be public. We don't want to give it public access. We want to control the public interface and make it as small and coherent as possible, easy to work with. So this will continue throughout this presentation. All right, so this is just an extension of what I just said about access levels and encapsulation. So in general, this is a design guideline in order to produce not just working code, but quality code. So your class has, you could simplify it and say public and private. So the public interface, obviously, as I said, you want it to be simple because it's exposed to the user and we just want them to get the object to work. That's a very simple idea. The internal implementation is complex inner state and logic, which makes everything work. So those might sound pretty straightforward. Here's just a you're not supposed to be able to read all this, or I didn't intend for you to read all this, but this is a real life example of a simple public interface and a very complex internal implementation. Obviously, I'm using the classic example of a microwave. So if you look at the picture of the microwave, very simple user interface. There's 5 buttons and a little knobby thing to turn. I guess you could kind of consider the handle on the door part of the public interface and also being able to read the numbers. So that's about it. That's the whole public interface. Um, as far as the internal implementation, I mean, just listing the items involved in the process is very complicated, like the transformer, the capacitor, the magnetron. Oh my God, the cooling fan, the antenna, the microwaves, and the metal mesh. It's like I thought I knew about physics until I looked at this picture. But even after even identifying those things is complicated. Let alone, I'm scared to know how a magnetron actually works. I'm gonna have to research that later. But that's the point, like if my mom had to heat up a piece of pizza by using the transformer and a capacitor and a magnetron and a cooling fan and all that, she just, she'd lose her mind. But she can easily press a button, turn a knob and press a button. So, I mean, that's all there is to it. So that's that. And this whole idea is sometimes called encapsulation, information hiding, simplifying a public interface, or an API, application programmer interface, or something like that. All right. Now, this is where it gets fun. Um, some languages actually separate the different patterns and variations of methods out into very specific named things. Like you'll notice that I stumble over going back and forth between methods and functions. Well, some languages make a distinction, and I actually like that. Like in Visual Basic, you have functions and subroutines. C# doesn't have that. Everything is just a method in C#. So I've tried to quantify what these different patterns are in a way that I can just start call everything methods from now on. And we've already talked about some of these things. So there's the getter pattern, which is basically just like it's a method that just returns a private variable. So it's like this variable is private. I need the value. Give it to me. So that's kind of the getter pattern. And actually, I'll jump down to the setter pattern. The setter gives you public access to change an internal variable. And that, when I say no output, that equates to the return type being void. So while a getter would, if you were trying to get at a person's age, it would return an integer, right? And it would have no parameters. So you would just say, hey, give me your age. So it doesn't have any parameters, but it does return an integer. With a setter, it's the opposite. There's no return type. You're saying, hey, I'm changing your age to this, and you provide a parameter value. So there is a parameter, which is the new value, but there's no return value because you're just telling it to do something. You're not waiting for it to give you a value back. And the getter and the setter kind of go together. It's called like the get set pattern. So if you have a private variable, usually in some languages where there's not something more sophisticated, like properties in C sharp, which I haven't gone over yet, but in Java in particular, you almost always see a private variable, a public getter, and a public setter. A computed value would be something more like, hey, figure this isn't stored anywhere, so I want you to just figure it out for me, what the value is right now. It might change in a minute, but I want to know what the computed value is right now. It may be completely based on internal state, but since state changes, it still is subject to have a different return value the next time you call it. So if you say, hey, object, how old are you? And it says 10, the next time you ask, they could have had a birthday between those two points in time. So that's why it's considered like a computed value. So to explain it a little better, I'll just move on to the next one, which is, the idea of a pure function, which I talked about before. A pure function is basically defined by the fact that it is not relying on state. So if you ask an object, hey, I want you to tell me how old you are plus 5. That's not a pure function. A pure function is, hey, what's the square root of 56 or something like that, right? You give a specific input and you get a specific output deterministically, and it doesn't change anything, doesn't have any side effects on the state of other objects. That is a pure function. So computed values, in contrast to pure functions, are not governed by that rule. So they can be based on stateful things about the object that you are asking to perform the behavior. So, hey, how old are you? You know, 18. How old are you now? Still 18. How old are you now? Oh, now I'm 19. So that's kind of a computed value. It's subject to change. Um, a subtle difference between a getter and a computed value. Getter is usually just a plain state access, and a computed value is usually something that you're pretty sure is going to be different every time you ask for it. So I hope that's clear. Um, and these are just semantic things. Like, these aren't, there's nowhere in the language where it'll say getter or, computed value or anything like that. These are just academic terms that we use to describe the different types of methods. So, but as you're talking design with other programmers, you should be able to say, talk about things like this. You could be like, this particular method is a computed value. Every time we call it, it's going to be, the return value is going to be reliant on these, 5 different things that are all constantly changing. So, we need to recompute it every time we invoke it. So it's important to understand at least the concepts, which is why I'm starting off with the concepts, kind of agnostic of the code in its entirety. So I kind of default down to the bottom one with just like subroutines, because honestly, when you get into void methods in object-oriented programming, you never really know from looking at the name and the signature of the subroutine what it's going to do. You really have to look at the code. So, my description here is any void method. That's pretty much it. And so it may or may not change the state of itself or other objects, right? So, this is basically this last bullet point is me saying basically a method can do anything. There could be patterns I'm not talking about here. You could pass another object as a parameter to, your object's method, and then in the middle of that method, call a state altering method on the object that was just passed in. So, you can a void method can change itself. It can change other objects. It can not change anything. Um, this is one of the criticisms of object-oriented programming. These things are called side effects. Basically, state changing in unpredictable places because of a call to a particular method. So here are some of the different variants. Like I said, there's kind of an endless number of variants of methods, but here's the typical one that we're used to, the function, right? So as you can see here, this is what we started off with already. Um, it was the person has an age internally. That's part of the internal state. And it says this object you can ask this object, hey, I want you to give me your age incremented by this number as well as this number. So two numbers. And as you can see in the body, it says return this dot age plus x plus y. So once again, um, this is a function. In math, if we said, f of x comma y, we would say it's a function of two numbers. Well, this is a function of three numbers, two of which are given to us and one of which we already know, which is our age. So it's a function of x, it's a function of y, and it's a function of our own age. So that's why object-oriented programming is a little complicated for people to understand, because there's context involved. It's not just a mathematical function, it's part of a bigger thing that has state. So I not only have the parameters passed to me, I also have my own attributes that I can factor in. So that's kind of the big thing. That's the big thing that is the light bulb, so to speak, in object-oriented programming, is to understand that everything happens in the context of an object, and the context you're in, you have to always be aware of it. If you're not aware of the context that you're currently in, then you're going to make mistakes. That is the absolute core of object-oriented programming. So this is the function example. It has inputs, it has an output. Obviously, that's the definition of a function. It has inputs and an output. I have a note here. It may or it may not be a function of internal state. This example, so that's what I was just talking about. This is an example of a function of x, y, and age. Now I have two examples here that I call value variants. In a function, a function has inputs and an output. And the reason that I'm calling these value variants, it's not a hard rule that they can't have parameters, but I think these methods with no parameters are a very good example of things that are clearly not functions. If there's no parameters, it's not a function, or at the very least, I guess you could say it's a function of the object's state. Like get age is, of a function. It's a function of age. So if age changes, the result of the resulting return value changes. But that's a stretch, In my mind, it's not really a function. It's a method that gives you public access to an internal, private, or protected member of the internal state of the object. And age is a pretty good example because not everybody wants to tell you their age. So before I move on to the computed value, I just want to draw your attention to the first line of code where I'm creating a public const int min voting age. The reason I did that is because I wanted to give you a better example of a computed value. So this last method down here, compute years until can vote, this is a function of this object's age, which is subject to change because people can get older. And it's also subject to what the current minimum voting age is. Before we just had examples of parameters and internal object state. So we would say this is a function of x, y, and age. But here we are reaching way outside of the scope of this method. Keep in mind here, this is a single object. From the class person we've created, let's say 100 people. So there's 100 people standing in front of us, and we single one person out. and we say, hey, you, I want you to tell me how many years until you can vote. So the answer is going to be different for every single person because they all have different ages. We know that. But inside of the logic that's computing this value, it doesn't just rely on their age. It also relies on this other value that is known, but it's not known in the context of the particular person we're talking to. It's known in the context of people in general. So that's why it's static. When you're trying to compute something inside of a method so that you know what value to return, what exactly do you have to work with? Well, you're an instance of an object, so you have any parameters that were passed to you. You have your own member values, and you also have access to some other things. Like here's one example: is um, that value that's just sitting there publicly available on the class. Person.min voting age can be called from anywhere, even another class. So you could be writing a completely different class and refer to person.min voting age pretty much anywhere. It's kind of like a public variable, as long as the library where that class is written is included. So just think about what we call the scope, that being what do I have access to here. Usually if there's parameters, uh, you know so usually there's parameters, and if there's parameters there, those will exist until you reach the end bracket. You always have access to the member variables like private int age, and you always have access to public static variables like min voting age. So what else have I said over here? Note, you can but should not alter the state when there is a return value. So I've said this, I said this before actually earlier, but let me say it again just to pound it home. Um, the programming language is not going to stop you from doing dumb things. So in the method getAge, where I'm just saying like, hey, tell me what your age is, I could write a line of code right above return this.age that also says this.age equals 99. So that's not going to get me the person's age. That's going to, every time I call it, it's going to change the person's age to 99 and then promptly return me back the number 99. So, it's important to um, name the method well and have the method do what the name says it's going to do. Not just the name, but the entire signature. And we'll get to that in a second. But, pretty much the name should be the driving factor in implying what the method is supposed to do. And anything that returns a value in general, and this is philosophical, so you may disagree or run into a situation where you try to do it, but philosophically speaking, if there is a return value, the purpose of the method is to get something, not change something. Here is the part in the bullet list where I told you that like void methods can pretty much have like an unlimited number of variations. So a subroutine, which is a void method, does not have an output, obviously, because the return value is void. It might have inputs, so it might have parameters. It might not. It might modify or mutate the internal state of an object of itself, or it might not. So it's like you don't necessarily know, and that's where like good naming comes into play. So I think you'll see this pretty clearly in the bottom two methods. So the top one is clear, set age. That is clearly a follows the setter pattern, which its whole purpose is to change a value, right? I'm saying, hey, I'm changing your age, and this is your new age. Next one is set name and age, and that one I have said it's modifying multiple internal values. So this is instead of the common setter pattern, which is just like, hey, change this one thing, I'm just classifying this as general state mutation. You never know, it could have 10 parameters and be changing a whole bunch of stuff. But in general, when you see the name set, name, and age, without even looking at anything else, you pretty much know that you're going to be changing the name and the age of the object. So it is going to be changing the state or mutating the state of the object. So that one's also pretty straightforward. And then the last one is, hopefully straightforward, but like I said, you can do things that are illogical. Print name and age does not sound like it's going to change anything about my object, right? It just sounds like it's going to print things. And the way I've implemented it doesn't change anything. It just does some pretty printing of some internal values. Um, Now, it's a command to perform a behavior, print name and age, and it has no return value, so it's void. Um, so I'm not sure what to call it other than a void method. So you see where the problem is if you just say I wrote a void method, that's not enough information to figure out what it's really doing. So once again, naming is important. Signature is important to indicate what the purpose of the method is. When I see print name and age, I have confidence that it should not be changing any values. And if I see that happening in a method called print name and age, I'm going to say, why are you changing a value, a stateful value permanently in a method that's called print name and age, right? So this is, very useful for reading code and critiquing it. The method signature consists of three things: the name, the return value, and the parameter type list. So I guess we'll start with the code. So you can see I've hidden the implementation, the body of the method in Visual Studio, because the truth is you don't really, as long as it works, you don't really care what the implementation is. So if I look at these two and I say, what do these do? Now, of course, you could add documentation to them, but if you don't, you can still rely on the signature to, basically tell you what's going on. So since I've named the first method add two numbers, it takes two numbers as parameters and it returns a number. It's pretty clear that if I open that body of the method or the implementation of the method, I don't know how it's going to do it, but it's going to add those two numbers together and return it to me. And I expect it to not change anything about the state of the object. This object actually has no state. There's no variables, but even so, I expect this to do nothing but what it says it's going to do. Take these two numbers and add them together. There's nothing about the the command add two numbers that leads me to believe that the object needs anything other than the two numbers I'm giving it to add. It doesn't need any public statics. It doesn't need any member variables. I'm asking it to add two numbers and I'm giving it to them. So I'm expecting that to be a very simple, pure function. Uh, Two inputs and a deterministic output. Add three numbers, same thing. The only reason I put add three numbers there is because I want to make a point when it comes to the implementation. So when you look at the method signatures without looking at the bodies, or how, basically the, spoiler alert, the implementation is the how, but the method signature is the what. And that's usually good enough. Like, what does the calculator do? The calculator can add two numbers and I can add three numbers. That's it. So most of the time, all you really need to do is look at the signatures of the definitions. I have a very good idea looking at this class exactly what it does. It's a calculator. It can add two numbers. It can add three numbers. That's what it does. Just the public interface alone, just looking at those two signatures, add two numbers, add three numbers, that tells me exactly what it does. So craft your signatures well, name them well, um, give them parameters that are obvious as to what their purpose is, uh, choose your types carefully, that sort of thing. Now, once I expand these, I am revealing how we achieve the functionality. So the method body implementation, as far as what can you see in the inside of the method when you're implementing the body, there's any local scope. So if you declare any local variables, obviously I've already said you have access to any parameters that are passed. You have access to all of your member variables, even if it's a private method. So even if the method is not accessible from the outside of the object, the method body still has access to all of the internal variables. So you have access to all members. That includes variables and methods. And also you have access to all external public statics. We've gone over that. And also we've gone over that the method implementation is the how. So really quickly, the when I expanded the first body, it's exactly what you probably predicted that it was. It says add two numbers, double x, double y. Big surprise, I'm returning x plus y. However, I wanted to show you that you never know how people are going to implement the method, and you really don't care as long as it works. I've implemented add x, y, and z in an interesting way that might not make sense to you. There's two things here. Like, there's one, I want you to understand that you can implement it however you want as long as it works. And the second thing is that I wanted to show you how sometimes um, having methods rely on each other is a good thing. So let's take a look at this. So the first thing I do is I say, okay, I'm supposed to add these three numbers together. And I say to myself, I already wrote a method that knows how to add two numbers together. So why should I write new code to do something that I already did, right? So I know it seems trivial to say x plus y, but that is defining logic. So I'm not defining logic when I say this dot add two numbers x, y. I'm reusing logic. Now there's a big difference. It might look like what I'm doing is more complicated with the sum of the first two. But what I'm actually doing is avoid writing the same code twice. That's called the rule of two. You never want to write the same code twice because that means that you're not reusing something that could be reused. And reusability is so important because it gives you one place where you can change it that will cascade to all of the usages. So yeah, definitely the what is important, but the how might be important if you ever have to um, change the way in how you're doing it, and the implementation is too complicated. So the moral of this whole slide is implementation is totally unpredictable, and it's up to the developer who's doing it to decide the best way to accomplish the task that is being asked for by the method signature. Method invocation, this should be no surprise since we've already done functions. The only difference is, so if we look at the two lines of code, double sum 1 equals add two numbers 10 and 15, sum 2, calculator to add three numbers 25, 25, 50. The only difference here between when we were working on functions and this is that we have calculator dot, which is exactly what we've been talking about. It's no longer just a function. It's now a method that is being executed by a very specific object. The only difference between method invocation in object-oriented programming is that it has context. It's an object that's executing it, and then in the body while it's executing it, it has access to all of that information that we were talking about before. So the method invocation has context. It may take parameter values. It may return a value. All those variations we talked about. I think we're almost done here. Managing object state mutability. Yeah, this is like the second last slide. What I've shown you in the code here on the left is boilerplate, private member variable, public getter, public setter. So I just thought this was a nice kind of just recap. It's something that you see quite often. It gives you an example of, it gives you a nice example of a class where the objects have a public interface, those two public methods, but they also have a private internal state. So when I execute that code in the bottom left, I instantiate a new student and I use my public method to set their internal S number to S007123455. That is how I change or mutate the internal state of the object. So this is a pretty very simple overview of the way uh, to define both void and non-void methods in the class, how to instantiate objects, and then how to invoke methods on those objects that you just instantiated. And to be able to kind of tell the difference between what's the public interface and those buttons on the front of the microwave and what they're actually accomplishing behind the scenes when you press them. This slide right here is a nice culmination of the core of object-oriented programming, is understanding that methods are really just functions with context, functions that are being performed by an object or class, by a class if they're static. Um, if you understand everything you're looking at right here, then you've done a fine job of getting started on object-oriented programming in this class. Just understanding the public aspect of things, the private aspect of things, understanding why you're creating a simple public interface, why you're encapsulating complexity, and the difference between defining a class, instantiating objects, and then invoking methods on them for whatever reason, whether it to be to look at information inside of them or to change values inside of them. All right, now we get to the very end. I know this is big, but I'm only going to talk about this for a second. I wanted to point those of you who are hungry for more information in the right direction. Um, you might have noticed that all of the method examples I've given you are very, very small. Every method that I've shown you has been very small. Most of the classes I've shown you are very, very small. Um, kind of the Bible of internal software quality is this acronym called SOLID, and the S in SOLID, as you can read, is the single responsibility principle, which reads there should never be more than one reason for a class to change. In other words, every class should only have one responsibility. And that the single responsibility principle can be extended to methods too. So let's go through these points that I just wanted to put in your brain, plant a little seed so that they can grow as you grow. Methods should be succinct to one purpose as opposed to monolithic and multi-purposed. If you find yourself writing very large methods that do multiple things, I would encourage you to think again and try to make them smaller. For complex behavior, you might say to yourself, well, I have to, it's complex. For complex behavior, you can chain smaller methods together by invoking each other, forming a larger composite. This is comparable to a complex circuit consisting of individual tiny logic gates. So you might look at a circuit board and be like, whoa, this is really complicated. There's no way I can do this simply. But actually, it's made up of teeny tiny things that are the simplest things possible. Like an AND gate has two inputs and one output, and the output turns on only if both inputs are on. So it's like this very simple little piece of hardware that only has one purpose. And by taking all these different logical gates and kind of combining them together, you can accomplish anything, like any type of complex logic. And it's the same with methods. So try to build smaller single purpose methods, and if you need to do something more complicated, try to combine them together so that you stay nice and uh, what we call cohesive, or there's a bunch of ways to say it. You could call it single responsibility, you can call it cohesive, you can call it just organized. So decoupled is another nice word we use to say. So a combination of small components into a larger composite occurs in many programming design patterns. And when you need to do something complex, you choose the pieces that you need and you kind of assemble them together into the larger thing that can do that monolithic task. So try to avoid monolithic code even for monolithic tasks. The metric which quantifies the lack of coupling and amalgamation is called cohesion. So that's what I'm trying to come across here is single responsibility equals cohesion. Amalgamation just means putting a bunch of stuff together, doing it all at the same time in one place, instead of separating them out. We're just going to do a quick exercise and then we'll be done. I'm going to run through the uh, as you can practice this yourself on your own, but I'm going to run through the method invocations here, or sorry, the method signatures here, and guess what they do by just looking at the signatures. And if I can do that, then I've done a good job. So first of all, at the top here, I have some static stuff. Obviously, so we're in the context of the idea of a person. So obviously, the static stuff is not about individuals; it's about people in general. So there's a number of people, there's a sum of all ages, there's a minimum voting age. So that's not about a person; that's about all people. Then there's two static methods, which also do not apply to individual people. Calculate average age and print average age. So this really gets into what we were just talking about. I have to look at those, and based on the signature, I have to decide whether or not what they're doing, if they're changing anything, without I don't. I mean, I can look at the code, but I can do it without looking at the code if I've done it right. So calculate average age, I'm guessing is going to fall into the realm of computed value. It's probably going to look at the ages, or wait, the sum of all ages, and divide that by the number of people and return that value. So those are two values that are constantly going to be changing. Every time I create a new person, the number of people and the sum of all ages is going to change. Therefore, calculate average age is going to compute a different value every time those change. So I'm going to open it up and verify that. That's what it's doing. It's dividing sum of all ages divided by the number of people, which are both subject to change, therefore making this pretty standard computed value. This next one is a void method. So that means it is either state mutating or just doing something. And, the print is kind of a dead giveaway. Unless I was a really bad programmer, I wouldn't be changing any values inside of a print method. So I'm guessing there's going to be nothing going on in here that does anything other than print to the screen. And there it is, system.console. There's no surprise going on here. These are standard. These look like textbook get set. So I'm just going to open these up, and that's what they are. So you have the private name, you have the getter, which allows you to look at it, you have the setter, which allows you to change it. And it's going to be the same for age. So you have the age, you have the getter, and the setter. All right, finally we get down to a bunch of these here, and this will be the finishing touch. So let's see if I can do this here. Get age incremented by x. So this has a return value, therefore it shouldn't change anything about the object. It should just look at our age, and it should be a function of our age and x, and just return the sum of those. Right, this.age plus x. Compute years until can vote. Okay, so that would involve our age and the minimum voting age. So there's no parameters. That makes sense because we know our own age. That's a member variable. And the minimum voting age is known to all people. So this is going to be a function of two variables, but none of them are parameters. There's the person min voting age, and there's our age. So that's good. That's a computed value. Get age incremented by. So this looks like a function. It's not a pure function because it's going to involve our own age, which is our state, which could change. And remember, a pure function is deterministic. It never, the same two inputs will always give the same output. Since we're including our age, that can change, therefore it's no longer a pure function. So this is probably going to be x plus y plus my age, which it is. Set name and age. This looks like a simple. For some reason, I wanted to provide one method that can set both the name and the age, even though I already have the ability to just call two methods: set name, set age. So this looks like a simple state mutation, changing the name, changing the age. Change the name, change the age. That's pretty simple. Once again, we have a print, which isn't going to change anything. There it is. And this is another computed value. It is just called can vote. So if I think about it, logically speaking, my age is going to be involved and the minimum voting age is going to be involved. So it's going to be a computed value which is a function, but it's not a function of parameters. It's a function of minimum voting age and my age. So my age and minimum voting age. If I'm at least the minimum voting age, then I can vote. All right, so that concludes this video. I'm sorry it was so long, but like I said, this is a lot of material, and I want you guys to have everything that you need. The .NET Fiddle code is there as well. There's a more documented version. So last week I gave you this quick introduction to methods, which was a much smaller, less ambitious attempt to get you putting your foot in the water but not swimming yet. And now, of course, I have this .NET Fiddle link to the code, all of the code that we talked about today. So this is everything that we just saw in its fully expanded form. So the link to the .NET Fiddle code that we've just been talking about is right here at the top of the class. This is the fully expanded version of all the code that we've just talked about. And luckily for us in Visual Studio, it has the nice option of saying outlining, collapse all the definitions. So that's how I quickly collapse them down to just the signatures. All right, that is quite long enough. I am going to ship this and hope that you don't kill me for making this too long. I will get everything you guys need up on Blackboard ASAP. I will create a not difficult assignment for you, as well as a quiz, and then I will look forward to a nice, peaceful Thanksgiving. And happy advanced Thanksgiving to everybody. I will wish you happy Thanksgiving again when I see you on Thursday night. All right, bye.